Hello? Yeah, everyone can hear me. Um, you'll be pleased to know I'm the last obstacle between everyone and beer, so I'll race through this quite quickly. Um, so today I'm going to talk a bit about building microservice architectures, specifically with Go, but this is a kind of general kind of architecture thing. Obviously, there's going to be a little bit of overlap with Neil's talk earlier, if you saw it, which is cool, because there's a lot of recurring themes, I think. Um, so So my name's Matt. I'm on Twitter here. This is a very huge screen, but somewhere over here. Uh, so if you've got any questions, I'll be around today, tomorrow, and ping me on Twitter. Um, I'm a back-end engineer primarily, so I've worked with distributed systems for quite a few years, specifically Go for the last 3 years. Um, Before my current job, I was working at a company called Halo, where we built a kind of on-demand taxi app. We ran across 3 different continents. We ran in 3 different Amazon regions. We used a lot of distributed databases because we obviously had to have high availability. And we moved from a monolithic PHP and Java application over the course of a year or so to a microservice-based architecture. And that was about 2, 3 years ago. And that was really interesting. We learned a huge amount, and then we've been able to take that with me, myself, and a couple of other people I used to work with, to the company I work at now, which is Mondo. And Mondo, we're building a new kind of bank. So this doesn't sound like the traditional kind of approach you'd use for like extremely new bleeding edge technologies. People have like banking is kind of stuck in this kind of age where you have branches and you go to branches and people send you a statement with your like list of transactions on, and that comes through the post. And now banks have moved online, except it's still essentially the same thing. You just have a list of things on your app, and that's considered internet banking. There's not really been any change there. And fundamentally, this is because their systems are like this. So there's huge amounts of mainframes, and they're running COBOL and all sorts of other systems, and they have to be extremely reliable, and they can't be changed very often. They're like quite literally the definition of a monolithic system. Now, on top of that, there are lots of banks using extremely new technologies that use like Docker and extremely other like scalable technologies, but they're only around the edge, and they can never really change these systems right at the core. And that's a problem, because for us, the world has changed. Everyone expects to get stuff on their phone immediately, real time. If I go and pay with my card, it should show up immediately in my app. It shouldn't take 2 days. So at Mondo, that's what we're building. So we're mobile first. We have kind of contextual information, so I can see where I actually bought things. This is directly from my app a couple of months ago. So I can attach receipts. I can search. You can actually search for emoji, extremely useful feature. But we can do contextual things, like we can do this month, and we can easily do things like that. That's like super easy for search. But we can also do things like contextual information for where you were when you bought things, and that allows us to detect fraud more easily. Or attach pictures to each transaction. So most people use this to take pictures of their receipts and then flag these things as expenses. I take pictures of my brunch, which I can do, and then other kind of features that you'd also really expect if you built something from scratch. So if you lost your card, you'd be able to freeze it, and then it wouldn't work, but then crucially unfreeze it if you find it again, which is a flag in your database, right? It's a bool flag, except in the UK, this takes 7 days to happen. You can't uncancel a card. You get sent a new one through the post. So if we're going to build one of these applications right from the beginning, where will we start? We traditionally start with like a large application, very simple. We do exactly what we needed to do, and as a startup, we'd build like the minimum viable product. And behind that, we'd have some form of database. It'd be quite nice and simple. And then over time, this is going to expand, and we're going to get a larger application, and it's going to get more complicated. And this is a kind of the story that lots and lots of people have gone through. Lots of startups have grown. They get to a point where the development team is too big to coordinate everyone working on one single code base. So we end up with more databases as we have more features, things like searching, caching, all sorts of other things that we need. And over time, our development process slows to a halt. I've worked on projects like this. It's extremely difficult to get changes in and then deployed. So your deployment frequency slows down because you have to spend longer testing each release, and then that slows down, and you end up in a position you're not shipping like by months. And this is really what's happening at this point. So we have a monolithic system, we're worshipping that, and this is my face when I have to work on it. And fundamentally, there's not a huge amount I can do. If I'm a developer working on that team, I have to get my changes in. I'm trying to deliver like business value and ship a product, except I'm constrained by my development tools. So the standard kind of thing that we've heard a lot over the last couple of years is starting chipping away at these systems. So we break sections off, and we can isolate those with a bounded context. We can have small amounts of functionality to do one thing and one thing well. And then at the end of that, we end up with a whole system of these systems. And this is essentially just a service-oriented architecture. As Neil mentioned, there's a lot of kind of very specific terminology around service-oriented architectures, whether these mean like enterprise service buses and all sorts of horrible things. In this case, all I mean is there are a number of applications which are coordinating across some mechanism to deliver our product. And these might be synchronous, they might be asynchronous, they might be event-driven. We can kind of build all of these things in because they're all independent applications, and we're not constrained by any particular technology on each one of those. So why would we start with a microservice architecture? So a little bit of background, Mondo has only existed for about a year. So we founded the company last February, and then over a period of about 3 or 4 months, we got debit cards working. And then over the next few months, we've kind of added additional functionality and launched into an alpha stage. And obviously, as a startup, you need to like nail your product. You need to work out exactly what customers want, and that means you need to get something into the market extremely quickly. And microservice architectures have a huge amount of upfront cost. So there's a lot of work that you usually have to do in order to even get a simple product working. But the reason that we did this was because we need speed. So in the UK, there's like 4 or 5 really huge banks, and they are massive corporations. Like Barclays spent £3 billion on IT in 2014. We do not have £3 billion worth of funding. Like we have no way of competing with that. So the only real advantage we have is that we're extremely small and nimble. So we need to move extremely quickly. And at some point, these large companies will realize what's going on, and they're already aware. There's a lot of really smart people who work in these places. And they will slowly change their business. And we need to be like a long way ahead of them before they can catch up. So when we're building these systems, we really start off with single responsibility principle. So every single one of our services, and Mondo we have about 90 at the moment, Halo have about 250. Each one of these, we're making sure it's doing one thing and only one thing. They're usually quite small, and as a result, we can scale them. We can understand exactly what's going on in that small box. And to do that, we're going to take our problems main and break that apart into a number of bounded contexts. So things like someone's bank account, that is one thing. Their customer details, like their addresses, things like that would be a different system. And we can break these things apart across those lines. And the nice thing there is if we're modeling this in a very kind of domain-driven context, we get really nice breakpoints. We get nice interfaces between these systems. And the result of that is that we get like really nice composability. And what I mean by this is that means we need to send push notifications. So we have a push notification service, and that has an interface that we can interact with. And that's it. I don't need to deal with like idempotence. Our service will deal with that for us. We can make sure if our APNS gateway is down, it will handle retries. And potentially it will do slightly more complicated things like exponential backoff. We might have jitter in there. But my other systems don't need to be aware of that. They just want to send a push notification so they can talk to that service and trust that it's going to handle that for us. So how would we start? In our case, we're going to start with a load balancer right at the top. And then behind that, we have some form of HTTP API. So crucially, we have a mobile app. We have to integrate with a lot of other third-party systems, banking networks, things like that. But our mobile app is just HTTP with JSON. So we need some way of terminating SSL and dealing with our requests. And then behind that, we're going to fire those internally over some form of transport. And that could be HTTP, might be REST, might be kind of a message bus using AMQP or RabbitMQ or something like that. And then behind that, we'll have a number of services which all talk to each other. And then crucially behind that, some of those will have databases, and those are only used within each one of their services. There should be no like talking from services to different databases. That's like a recipe for disaster, because it makes things really tightly coupled and it's extremely difficult to migrate. So in this case, what we've really got right at the top is actually an API gateway. And in our case, our API is dealing with things like rate limiting, and our services underneath don't really need to be aware of that. And it does things like takes messages off, and in our case, we actually use RabbitMQ behind this. So we take HTTP in and then fire that internally over our internal network. And the cool thing about an API gateway right at the top is that means you can do quite interesting migration patterns. So at Halo, we had quite a large application, and what we could do is slot in this gateway above that, and it just proxied all of the existing traffic through to the current thing, literally just reverse proxying. And then we could move that off to one side, and then we could introduce a number of our services. And what this API gateway was doing was taking particular routing patterns, matching on those, and then sending those off to other services, which allowed us to migrate straight over, just chopping away certain sections of our infrastructure. Now, in Halo's case, we took huge quantities of GPS points. If you know where if you've got taxis driving around, you take in like hundreds of billions of GPS points. And that's a huge percentage of our API traffic. So a really nice thing that we could do here is we could build the services that just handled that section, switch that over, and we'd already massively reduced our costs. And we could shut down like loads and loads of servers, mainly because we were moving from PHP to Go. So hands up anyone who's used Go here. 2 people. Excellent. So for anyone who hasn't used Go, Go is quite a new language. It's been about 6 years now. And it's got quite a few nice properties. So the language itself is really, really simple. There's a huge amount of other functionality that you can use, but the actual like language constructs and the syntax is extremely simple. And for me, that's quite nice because it means you can get up to speed really quickly. In some other languages, I find myself I write some code and it totally works, but then I'm not sure if it's the most idiomatic code. Maybe I should rewrite this in a slightly better way. And in Go, I don't really get that. Like, it's very straightforward and kind of procedural, but that's awesome. It's extremely simple to read through code bases, and as a result, like, it's really great for a development team. It's also statically typed, which if you're dealing with people's money is quite useful. So we don't have any floating point issues, which is quite nice, or kind of any type conversions, stuff like that. And also it's statically linked. And this means that you can take your Go program, you can compile it with this particular architecture, and then you can just put that binary, a single file, on a machine and run it. And there are no runtime dependencies. So deployment is extremely, extremely simple. On top of that, it has a really comprehensive standard library. So the standard library has all of the extra functionality, things like creating a HTTP server in like 3-4 lines of code. And it's really quite nice because in 1.6, which is Go 1.6, which is just launched, it has native HTTP2 support. So actually, if you had a Go 1.5 server and you now recompile it with Go 1.6, it will natively just upgrade your clients to HTTP2. I don't have to do anything. The garbage collection performance is increased in every revision. It's just really nice that those things are kind of built in. And particularly in microservice architectures, you have a huge number of network calls. So that the networking library is really good and does all your kind of normal things like connection pooling and keep alives and everything just like automatically. That's quite nice. But the main thing that you kind of hear about Go is its concurrency. So in Go, you can write a function and you can literally write Go and a space before it, and that will execute asynchronously. And concurrently with all of the other Go routines that you have running on your machine. And that will run across multi-core machines as well. So Go has a very efficient scheduler where it runs a small number of OS level threads, so 1 thread per core, a few others if they get blocked on I/O and things like that. And then it will kind of multiplex those Go routines across the OS level threads, and it just deals with all the execution for you. So you essentially have an extremely simple kind of threading model, but it's extremely performant because you're not using like OS threads. And then on top of that, you have really nice interfaces. So Go supports like kind of duck-typed interfaces where if you have a particular struct that has a number of methods, any struct that matches those methods, you can pass in. So you can switch out types, which is super useful for testing. And as an example, in our case, we have an abstracted transport, which we can plug in HTTP, we can plug in RabbitMQ, but we can also plug in an in-memory mock. So we can stub that object for testing, and we can run all of our tests in memory, which makes them thousands of times faster. So if you're starting building a microservice architecture in Go, there's actually a few frameworks you can use. So GoKit has been around for a year or so, and that provides like a really nice framework for kind of building out services. Micro is quite similar. Again, allows you to build clients and servers very easily, and there's a number of reference services, things like discovery and configuration that the authors have kind of put together. gRPC has kind of come out of Google and I think Stripe, and one of the really nice things about gRPC is a bit lower level, but it does things like streaming. So if you've got massive domain objects that you're moving between services, you can stream those, and you don't have to do the whole thing in a request response style. Unfortunately, in our case, none of these existed when we started building our infrastructure. So we have our own system. These are on GitHub, and they're open source. They're MIT licensed. And what these are doing is we have a library that provides an abstracted transport, and then a library on top of that that gives us a client and server. And we can configure these with like a number of kind of things like this is how you get configuration, this is how you do service discovery. So in our case, to go back to the previous example, we have a load balancer, we have our API routing layer, and then behind this we have a number of services. And these are like API services. These deal with our API functionality. So as an example, we have a webhook API. So you can register new webhooks on your bank account. Every time you use a card, you get a webhook immediately, usually before the receipt has printed in the machine, but it's not very hard to send things in like 200 milliseconds. So in our case, we take /webhooks on our API, and we route that internally to a service that is the webhook API. And the reason we do this is because all we have to do is deploy additional APIs. We have like this kind of routing pattern, and that means if I didn't have a webhook API before, I now deploy it, it registers with our service discovery. Our service discovery now knows it's there. Our API is polling this continuously, which now knows that there is an application capable of handling /webhooks, and now it will start routing that traffic through to our application. And what that means is that I can deploy entirely new sections of our API with zero impact at all to anything that is currently working in our infrastructure. And this makes our infrastructure a lot more stable. We don't have to change this HTTP routing layer right at the top. That's extremely stable, which is great if you're doing things like PCI compliance, where you have to do like lots of change control on anything that's kind of involved in that, the data flow that involves card numbers. And it just means it's much simpler. We can test things really easily. And then behind this is then going to send off requests to a number of other services. So the webhook API in this case is kind of acting as an orchestration layer. It's going to orchestrate calling our other services within our application and do things like authentication, and kind of our webhook service down here is actually the thing that stores webhooks in a database and listens to an event stream and decides when to dispatch them. So it's responsible for like just storing webhooks and just processing them. And we have a separate thing that's kind of responsible for orchestrating our API, which our customers are interacting with. And behind these then have their own databases. So they'll just use their own database entirely. We use Cassandra for almost all of our data, which means that we have eventual consistency, but it's more tunable. We can choose whether we want extremely high levels of consistency with lower availability, or actually we can deal with eventual consistency in a number of cases. And it also means we can very easily scale outwards, as Cassandra scales linearly with writes. But realistically, these services can do anything. So we might have a number of services, and they might do things like abstracting third-party APIs. And each one of these, again, is just a single Go application. It's a single binary that's running on a machine, and it's just connecting to our message bus and scooping up messages and sending back replies. So inside one of these, we have a service, and this is broken into like 3 main areas. So we have like the handlers right at the top. These are essentially just functions that take a particular message format and send a response. Behind that, we obviously have all of our business logic. And then kind of underneath that, we have all of these like abstracted service providers. And what I mean here is that like, if I want to write data into Cassandra and I'm doing application development, I shouldn't need to worry about where Cassandra is. Like Cassandra servers may go up and down, the IPs may change. All of these things should kind of be handled automatically for me, which means that I then can just write my code, deploy a new service, and I can have stuff in production within a couple of hours. And that's the kind of speed that we're developing at Mondo. So we have our Mercury library at the top, which provides this framework that we can slot function calls into. And then each one of these is just going to take a request and return a response and an error. So as basically no one has used Go before, this is a kind of standard type definition. So this is an interface in Go. So we have a type called handler, and that type is a function that takes a request and returns a response and an error. And in Go, the kind of convention is that most functions return multiple values, and the last value will be an error, which may be nil or maybe some kind of error type. So this means that any function at all can satisfy this interface as long as it takes a request, returns a response, and an error. And we can build like a lot of very flexible things off the back of that. And then underneath, these then go into our transport. And again, our transport is an interface, so we can use any number of different types that again satisfy a particular interface, which would be something like this, most of which is completely irrelevant. But the important things are that it can do like these 4 things. So we can start listening for messages, we can stop listening for messages if we're going to shut down, and we'd want to shut down gracefully, so we'd stop receiving new ones, we'd reply to all the kind of in-flight requests, and then shut down the service. We need to be able to send new requests if we're requesting another service, and also respond to our inbound ones. And because, again, this can be any type that satisfies this interface, when we're testing, we can just switch this out for essentially a map that is wrapped in this type, where we would put a request in, and our response would be to take it back out of the map. So behind this, we have our service, we have all of our business logic, and then our storage is kind of abstracted into a number of libraries. And Neil mentioned like this kind of moving a lot of this development out into like kind of platform teams. And that's something that we do really. We have a lot of core libraries in a service template, which this is. And that means that we can improve the kind of the reliability of all of our clients and our database connections and how we handle requests. And then we can just rebuild these things with the latest version of the libraries. And our services become more resilient and more reliable over time. And these things do like a huge number of things that everyone talks about when they're talking about microservices. So in Go, we have really nice deployment. We have a single binary that we can put on any server. When these services come up, they're going to register with a central discovery system. In our case, we use Zookeeper, that we have like a service that wraps around. So Zookeeper is a really nice, consistent data store, but it doesn't really provide much above key value storage. So we have a service that deals with services registering, and also the fact that you need to like heartbeat. They should only have a particular lifetime. And if a service hasn't reported that it's healthy in a particular amount of time, then that should expire, and we shouldn't communicate with that service anymore. Again, things like configuration, our monitoring systems are plugged into this automatically. So if you use a database, then that means you're using our database driver from our service template. That already has monitoring hooks built in. So that means if you deploy your service and you haven't actually created the key space or the database in your database server, that'll flag up automatically on our monitoring systems because we have tests built in to make sure that you can read and write to and from those databases. And all the other things, so circuit breaking is a really interesting one, which I'll come on to in a little bit. And then as far as deployment goes, as I mentioned in Go, this is really easy. So we have a single binary, And if that's compiled for like 64-bit Linux, then I can put that on any server. Obviously, there's a lot of tools around this. So the main one we all hear about really is Docker. And Docker's great because although in Go you have a binary, so you don't have like all the runtime dependencies and the kind of repeatability that Docker gives you, you do get a lot of other things. You get all the kind of, you can limit the memory and CPU usage, which you could do natively using C groups, but with Docker you get for free. You also get a whole ecosystem of tooling. So it's really easy to just take your binary that you've compiled and put it in a really simple container. So you don't need like an entire Ubuntu container. Who uses Docker here? Few people. Hands up if you use like full Linux images or use small ones. Okay, a couple of people. So the difference here is like shipping around a container that's maybe a couple of 100 megabytes, or a binary that's 5 megabytes with a container that makes it 15 megabytes. It's a lot easier. And there's a couple of really good ones. So you could use BusyBox, or if you need a couple more tools inside that, you can use something like Alpine Linux. But again, those are really small containers that you can just ship anywhere in your infrastructure. As I mentioned, statically compiled. So there's no runtime dependencies inside the container, which makes deployment super easy. But there are still a couple of things to bear in mind. If you used a Scratch container, for example, which has nothing inside, it's a blank image, you don't have root certificates inside. So you'd need to copy those into your container before you ran your binary. Otherwise, you can't do TLS, which for a bank is quite important. And now once you have your containers, you can then ship them onto any number of platforms. So we actually use Mesos with Marathon as a scheduler. And that means that we have a kind of aggregated compute power across a number of availability zones in Amazon. And we can apply constraints. So we'll never run more than one copy of a service per instance, or we'll run at least 2 per availability zone, things like that. So we can get an even balance across the availability zones, and we can make sure that a single node failure won't take every copy of a service out. So given that we're running on systems such as Amazon or other cloud providers where our infrastructure is constantly shifting underneath us, how do we make our service more reliable? So there's a lot of things that we can do, but in a lot of cases we have extremely low latency requirements. We have to reply to, when you use your card in a card machine, we have about 100 milliseconds to reply to that, which in Go is super easy. Like, that's fine, but we need it to be reliable, and so our distribution of response times has to be quite tight. So the way we get around most of this is by pushing everything that we can to be asynchronous. So we use a lot of event-driven things within our infrastructure. And by this, I mean, given a kind of synchronous call path, this would be charging a card, for example, there are a certain number of things we have to do immediately. We can't make them asynchronous. But the end result of this is that we can push a lot of those things via an asynchronous event bus. And then any number of these systems can listen to these and then do further actions off the back of that. So a good example would be something like Kafka, or we use NSQ, where we can publish events onto a durable message bus, so we know that they will get actioned, and then any number of subscribers can read these. And the advantage there, again, is that we can deploy new services to add functionality without impacting any of our existing architecture. So we can test things out really easily. The downside of this, of course, is that you end up with something like this. You have no idea what's going on. And I mean, we only have like 90 services at the moment, but we're running multiple copies per availability zone. We run across 3 availability zones. At some point in the not too distant future, we'll run across multiple Amazon regions. And keeping track of every single instance of a service is essentially impossible. I certainly can't keep in my head of where all these things are or how all of our systems work. And we've got quite a small team still. So this is only going to get worse in the future. So we can get around a lot of these things with kind of topology management, and we can do all of this automatically. So we can use things like service discovery so that we know which services are available, which services are currently in a degraded state, or which instances of each service are the fastest performing. And if you're running on a cloud provider, then some instances, like some of the servers, will be lower performance. And I think I saw something that Netflix used to do where they would test instances when they came up and then kind of kill the ones that were really like really bad performance and just get a new instance and test that one and see if it was better. We don't have that problem yet, maybe at some point in the future. But what we do have is things where services fail. And this is a problem because in the case of this call failing, then that means our API will fail and will return errors back to our clients. And if we had a very naive approach here, we might be doing like a round robin across all of the available instances. So we, at this point, get 1 in 3 failures at random. And that's not great. Like, there are a lot of ways we can make that better. So if we can detect failure, we can spin up new instances, and then we can change these in our clients, in our service discovery, so that our clients are only sending messages to available, healthy instances of each service, which is great. But then you have a slightly different problem where some of these are really slow. So in the case of a particular one, it might be like, it might have transient network problems. So some of the calls might work, it's still checking into our service discovery system, it still thinks it's okay, but actually it's significantly slower than any other copy of that. And we need ways to be able to test for this. So if you've used things like circuit breakers, you can kind of, so Go has a really nice circuit breaker implementation. There's definitely a couple in Java and Scala. And the way this usually works is you'll have a number of hosts, and every time you make a request, say a HTTP request, you'd check out one of these hosts out of a library, you'd use it, and then check it back in with either an error or not, and how long it took. And from this central library in your service can keep track of which the fastest copies are, which ones have errors. So if you have a particular copy that just has lots of errors, you might stop sending it requests for a certain period of time, which is a circuit breaker pattern. But if you do something a little bit nicer, then you can actually preferentially send requests to the fastest instances. And what that'll mean is you could have all copies of the services in a region in Amazon available, but you usually preferentially send them to the ones within your availability zone, or even locally on the machine if you're co-locating services. So you can use something like an epsilon greedy algorithm, which will preferentially select fastest services out of these. The other way to deal with tail latencies is with fan out and cancellation. So Neil mentioned how Google search works earlier. So when you type something in, you search, and it gives you, one, an extremely fast search result, but also, like, if you've typed something in slightly wrong, it'll give you possible corrections. And the way that you can do this is by firing off lots of searches in parallel. And you can do that even if you are still doing the same thing. So if you have something that's cancelable, you can send a request to a particular service. A few milliseconds later, send another request to a different service. So now you've got 2 in flight. Bit bad. And then you can send a third one maybe. And at this point, you've now got 3 outstanding requests. Now, some of these will probably return really quickly. But if you maybe have your client set to timeout at the upper 95th percentile, then that does mean that some of those times it's going to come back really, really slowly, and your client will time out. Whereas in this case, we might get a really fast response from one copy of the service. And at that point, we can cancel the 2 outstanding requests. So this is something we can do actually in our Go libraries. And the way we can do that is by passing essentially request IDs throughout our system. So we can say, here's a request. Oh, now cancel that one, but don't cancel that one. However, in Go, that's actually a little bit tricky. So we have like a context that we need to pass through on every request. But Go doesn't have thread local variables. So you can't store like a request ID and then just pass that all the way through. You have to pass that as an object. And Go has a really nice context pattern. So again, it's just an interface, and it's some kind of object that has a number of methods. But the crucial one here is this done method. So when you call done on a context, what this is going to do is return a channel with a struct. And this is just a channel of like blank objects. And channels are a really nice way that you can communicate between Go routines in Go applications. So this channel will send a struct, it'll receive a struct down the channel when the context is terminated. So you can implement this in an application where you get a request, that's gone several levels down in your application, and then you still have a copy of this, and you can cancel it. And then all the way down in your application that will return and just stop doing work at that point. So given that we have quite a complex infrastructure, we then need to be able to test this. And this is something that, as we're dealing with people's money, we're dealing with kind of low latency payments, things like that, it needs to be extremely reliable. So there are a few main things that we're testing for, really. Obviously, load testing. I'd recommend doing that. Capacity planning, super important. But then also failure testing. So things like using Netflix's Simian Army, where you can terminate instances, copies of services, things like that, and make sure that your application still works as a result. And then the thing that I normally see the problems with are when you have degradation of these. So when you have higher latencies in particular applications and you haven't configured timeouts in other sections of your application correctly. So this is something that I would strongly recommend if you have tests that you can run them. And you can hook these into your monitoring systems as well. So all of our services in these service templates register callbacks that send data, monitoring data constantly to our monitoring systems. And that means, again, as an application developer, I can build a service really quickly and everything's already built in. I don't need to worry about kind of building in monitoring hooks unless I want custom ones. And then we have a framework that allows you to do that. So the nice thing really is if you have monitoring systems, you want to be able to test that the actual things that you're expecting to work do work. So things like card payments. So who has acceptance tests in their application? No one. Please, everyone has acceptance tests. Come on. Okay, a few people have acceptance tests. Everyone else, homework, write acceptance tests for your application. You should definitely have them. And in our case, we have acceptance tests, and they work with essentially fake customers and fake cards. And what we can do is we can assert that not only our acceptance tests work in our build pipeline, and they work locally on my machine, locally on our build system, but also when we've deployed them into production, we can run these again continuously. So we have real cards that are doing real payments constantly throughout the day. And that means that what we're really doing is we're testing all of the functionality that customers know about. And as long as our acceptance tests work in production, that means we're up. That means the customers are unaware of any problems. So even if we have database failures or servers that have run out of disk space or crazy latency between different sections of our application, as long as our acceptance tests run successfully, then our customers are unaffected, and we can be very confident of that. And crucially, that's important for us, because if you go to a cash machine and your card doesn't work, then you're going to be really, really angry, and you're probably going to switch banks. So it's crucial that these kind of things work all the time. So we have two kind of monitoring. We have, as I mentioned, out-of-band stuff, which is outside of our infrastructure, that is kind of continually testing that our application works. And then also in-band testing. So these are things built into the services where they're pinging, checking that the transport layer is working, checking that they have a connection to the database, checking that they don't have too many connections open to an external supplier. Maybe if we've kind of got a bug in our connection pooling logic and we're just establishing hundreds or thousands of new connections constantly. And again, in Go, you can do this really easily. So we again have a type, which is a function that returns an error. So it can be any function. And in Go, you can do closures. So you can pass stuff in, get a custom checker back, and then we can plug this again into our monitoring framework. And all this is going to do is execute it periodically. And if it returns an error, then we have a problem, and it can put that into our monitoring systems. So on top of that, again, we have lots of other tools that you can use to debug performance problems and all sorts of other problems that you have with quite distributed infrastructure. And one really cool tool is the ability to do distributed tracing. So has anyone used Zipkin? Or yeah, cool, a couple of people. Implementation of the Google's Dapper paper. And there's a few others like htrace and a couple of others. So what this is really doing is allowing us to get really good insight into what happened on a particular request. So we can aggregate these and get an overview of our system, but we can also debug individual requests, even though they've gone through 20 or 30 different systems. And the way that we can do this is, given kind of a sequence diagram, we start right at the top of our API, and we'll generate a random ID for this request. So something like a type 4 UUID. So completely random, and this will then be passed all the way down through our application stack. So we'll pass it on here. When it gets to when it leaves the API, we'll take that request ID, we'll marshal that as headers on the wire, send that across the wire, and then unmarshal it from the headers back into this context object. And then when we send off another client request, we can again take our context, we can marshal that onto headers, and again send that down to the next service. So that means that every service has this unique request ID, and we always know which request we're dealing with. And then, again, we're using this context interface. This time we're actually using a slightly different functionality, so it has a key value store. So you can put a key of any type, and you can get back a value of any type. So the interface is essentially like represents any type in Go. It's a blank interface, which means any type kind of has all the methods that a blank one does. And when we then get this return path, we can at each one of these points send like tracing data. So this is like instrumentation data about whether we got an error, if we've sent a request and got a reply, if we timed out, how long it took, the service instance that handled that request, the machine that they're on, all those kind of things. And we can aggregate all of that data together into a central system. So you could use Zipkin. We have an open source one called Phosphor. And the end result of this is something ridiculous like this. And it's like megabytes of JSON sometimes. And this is completely unintelligible. Like, I have no idea what's going on here. But we can take all of that and we can reconstruct what happened on a particular request. So this is an example from our production systems. So this is someone in a shop. They've used their card, put it in the card machine, and charged their card. And we do a lot of things off the back of that. So we have our API. Hello? All back up again. So we have a synchronous call to our card processing service. So we have a card API that is taking all of our card payment requests. We pass that down then to another service that kind of understands how those work. So the top level is actually, in this case, dealing with XML, and it's basically a SOAP server because banking networks use SOAP. I mean, a lot of them, like SOAP is quite advanced, so great. And then we pass that down to other systems. So we're going to look up and see whether the card actually exists. And if it does, if it's not been blocked or turned off temporarily, then we can carry on down. We can put that into our transaction system. And we do a number of other things there, but the end result is that we do all of this section synchronously, and then we can respond back to our card processor. And as a result of that, we publish an event onto a durable message bus. And then everything else from this point is asynchronous. We can do this whenever we need. If our services are down, we'll just pause them and they'll queue up. And we can process them later. And we do everything separately. So when we take in a card payment, we actually go and look up like merchant data. So if you go and use your card in a petrol station like BP, then we'll identify that and we'll go off and do things like get the logo from Twitter. We actually have a whole system that kind of aggregates that, and we vet them and make sure that they look okay. And then the result of that, we publish another thing asynchronously. And this goes into a separate service that actually sticks an item into the app. So in the app, we have like a feed of transactions, and it's the actual point that that's slotted into the app and visible to the customer is entirely asynchronous. So if our systems were down, their cards would still work, but their app might not update, which is preferential to their card not working at all. And then as a result of that, we then send them a push notification. And again, that is asynchronous. If we haven't processed it within a short period of time, then we cancel it. But again, if our systems are down, if our APNS gateway is not working, then we'll re-queue these and try them again. So this sounds like it takes a huge amount of time. And basically, we get this at the end. So we get a coffee cup because this was an espresso shop. We know exactly how much it was. We actually do the currency conversions in real time. But we have that contextual information. And actually, we can do this in like 200 milliseconds. It's really, really easy. So in the case of using your card, banking networks are really slow. Like, you use your card, and it takes a few seconds before the till has accepted the payment, and then it takes a couple more seconds, and then the receipt prints. Whereas we can get something to someone's phone in, a couple of hundred milliseconds. So 90% of the time, we actually beat the receipt machine. It's really easy. Like, that's really not very hard to do on, like, modern systems. Except this isn't really what we do. We do something that's a bit more like this. So the end result of this is I use my card and my phone buzzes before the receipt prints, or sometimes before I get asked if I'd like a receipt. And the cool thing again is because we have this request ID at every stage of our application, we can actually look up log lines. So every log line we write in our application, and we try not to write too many because logging is extremely expensive. I don't know if anyone's used things like Kibana or Logstash. Cool, yeah. If you stick 10 billion log lines in that a day, it doesn't work. Like, it's really hard to scale. But we never really need to search like across every log. We need to search for specific log lines that are interesting. So we have different levels like error, debug, info. So we can throw those away. Like, we could throw away debug lines really quickly. We can keep errors or more serious errors for a much longer period of time so that we can investigate them. But also, this is for one particular request. So we have every log line from this request, even though it traversed 10 different services across 10 different physical machines. So these are in 10 completely different log files. And again, that's quite easy to do because all we're doing is looking up by a single key, which means we're doing a key value lookup. And in our case, Cassandra is really good at that kind of thing. We can also do aggregates. So in our case, we can also generate diagrams like this, which are pretty but not very useful. But they kind of convey the kind of complexity that you're dealing with and why with microservice architectures you need a lot of tooling to be able to debug these problems when you have them. So this is an example where we've got the width of the line is the amount of traffic, and then the color is whether it's healthy or not. So there are a couple of failures in here. Hopefully everything's okay. So if you're starting building a microservice architecture, should you use Go? I mean, obviously I'm quite biased, so I'm going to say yes. I think it has a number of advantages. It's really easy to learn because the language is so small. So it means you can be productive in a really short period of time. Because of the language features, it's extremely good for microservice-based architectures. You have highly concurrent services that can do, in some cases, 10 or 100,000 requests a second on a single process. And it scales linearly with the machine pretty much. So performance-wise, it's really good. As far as downsides go, there are obviously downsides. So Go historically hasn't had particularly good dependency management. So there are a few alternatives now, but that does currently mean that you have lots of third-party libraries, and you'll have to copy all of those into your repository, which is less good. Also, because the language is quite relatively young, the quality of those third-party libraries is quite variable. So at Halo, we were stuck for about a year maintaining our own Cassandra driver, which is not ideal. And thankfully, times moved on a bit. So like most of these like database drivers are actually really, really reliable, but there are still libraries that just don't exist or of quite poor quality. So should you start with microservice architecture? I'd say probably in most cases, it's still not necessarily the best thing to do, because the main problem you have, certainly if you've just started a new company, is understanding the problem that you really have. And unless you understand like the business problem, it's very difficult to break your business problem apart into the right kind of level of service. So you'll get those abstractions wrong, and because of that, you'll have to rewrite things, throw things away. And if you're in an extremely early stage company, that's a lot of extra work. But if you've already kind of built your application, if you know how that works, then you can make far better decisions about that. And at that point, that's a really good time to start like chipping away and breaking your application into much smaller parts. And that's about it. Thank you very much. Does anyone have any questions before we drink lots of beer? Yeah.
How do you get the information about someone paying with the card?
What kind of information?
I think I skipped the first 5 minutes.
Yeah.
Maybe so you said you get information on your application before the receipt is printed.
Yes. So the question is how we get the information about cards when we use them. So we actually issue our own cards, which look a bit like that. So we have a card processor. We're in the process of becoming a bank, so in about 6 to 9 months we should get full approval to become a bank. And until then, we have a card processor who we've interfaced with. So we're in the authorization loop. So when I charge the card in a machine, we get a real-time synchronous request from our card processor, and that's like a SOAP request. Pardon? And as a result, we get a small amount of information, things like the postal code, the name of the merchant, kind of stuff like that from the MasterCard network.
But the merchants need your card processors.
No, it's standard MasterCard. So it's a normal MasterCard. We get a small amount of information from MasterCard about that transaction, and from that we approve or decline it in real time as a card processor. And then we have an asynchronous pipeline which then takes the small amount of information and does things like look up against Foursquare, Google Places, all of those kind of other like location-based services.
You get this small amount of information within milliseconds.
Yes. So our card processor has a 200 millisecond timeout on their end, and during that, that's got to come across a VPN, negotiate TLS because they're comparatively few, so we don't have a lot of established connections, and then we have to do all of our internal processing and return within 200 milliseconds. So we have about 100 milliseconds on our side by the time we've done TLS and all those other things. Anyone else? Yep. Yeah. So we have our own system, which is open source. So it's very similar to Zipkin. So the question is how we aggregate all of these things together. So bearing in mind we have a request that's traversed, let's say 5 systems synchronously, and then we've published an event as a result of that, which has now triggered an unknown number of other things that happened at some point in the future. So we pass the request ID through our event bus as well. So every touch point has that UUID. And then we publish that onto like an internal event bus, again, that just aggregates that. So every touch point, even if it's synchronous or asynchronous, we publish that data. And we have a separate service which then aggregates all of that and stores it in Cassandra currently. So the important thing is we're not doing full text searching. The only searches we're ever doing is by the UUID. And in Cassandra, that means you have like a wide row, and you can just put every single event into that and pull it out very, very quickly. I mean, yeah, it means we're doing like maybe 10,000 writes a second on that, but we can throw the data away very quickly, so it's not a huge problem to store it. But yeah, Zipkin will do the vast majority of that, and let's be fair, has much better tooling, but it doesn't do any of the asynchronous parts, which are extremely important in our systems. Anyone else? Yep.
How do you avoid data loss, especially in the financial part?
How do we avoid data loss in the financial parts? So we use, as I mentioned, we use Cassandra, and Cassandra is really nice because it has tunable consistency. So we have a number of Cassandra nodes, and for everything that is extremely important, we can write that at a very high level of consistency. So we can actually write to all of the nodes, which guarantees that you've written it, but that means that if one of the nodes is down, you can't write. Or you can write to a quorum of nodes, which is far more important. So On our cards, actually, at the moment, our card processor is the system of record, which means they hold the balance officially. We hold the balance internally. When we become a bank, we need a fairly consistent data store to store people's money. But until then, actually, we can do most of these things at a quorum level right. My experience with Cassandra is actually if you write a quorum, you have quite a reliable source of data, and you can tune Cassandra as well to do things like immediately sync the data to disk, which lowers your write performance, but it means, again, it's more reliable in the case of like process crashes. As far as consistent data stores go, obviously you can use any number of large enterprisey databases. Or things like Postgres, where you have serializable consistency. The problem then, again, is you have problems with replication and node failure. So in our case, actually, there's really only one system, which is like the ledger of all transactions of money, but not the metadata. So just like literally this account moved that money to that account, where you have dual booked accounting. That's the only part that has to be actually consistent. And even then, the choice of consistency is really a risk to the business that we would be operating on. So yeah, we can use some consistent data stores, but actually just behind one service, and most of the touch points that are asynchronous. So if it's down, it's less of an issue.
And the routing part is persisting the events, or will it get resent when something is done from this persistent first service?
So in the case of the consistent data store, do you mean?
So a transaction comes in,
Yep.
you store it in a quorum level database, right? And then you start your asynchronous processing, and something goes wrong. You need a service and it's not there
Mm-hmm.
for a long time. What happens?
So in our case, when we write something onto an asynchronous message bus, if you use something like Kafka, then you have they're durable. You can write again to a quorum of nodes. So we use NSQ, but we write to a quorum. So we actually publish each event multiple times and only acknowledge success once we've achieved that. And what that means is, although we have duplicated messages throughout our system, both Kafka and NSQ are guaranteed at least once systems anyway. So you have to handle duplicated delivery. So in our case, we might get a message 2-3 times, and we'll just make sure that we process that, either using something like a distributed lock, so we use etcd for our locking, but then that adds a lot of additional complexity, so we try and do that as infrequently as possible, or we make everything idempotent. So a lot of operations in our system are idempotent. We can deal with those being retried. The message bus itself is durable and will retry, and that means we might pause a particular service or a whole section of that event bus for a day, 2 days, if we had a serious problem. NSQ does exponential backoff per message, so it deals with a lot of that for us. Cool. Anyone else? Yep.
You were talking about backup requests, sending multiple requests.
Yep.
Are those requests only queries for reading data, or are you also modifying state? Because you need to then, how do you do the
So in the case that they're reading, that's really easy. Yep, we can just send lots in parallel. In the case they're mutating state, we now have race conditions. So in the case that we do that, to be honest, most of the ones where we're reading, we want higher performance. In the case that we're writing, we would still be using something like a distributed lock, but that means that we use the retry mechanism less often, because that means that we're always blocked, waiting on that lock to expire. So yeah, mainly for the read path, to be honest. And if you're dealing with most of our writes are actually quite low volumes of data. Say 60 quite quickly. Yep.
I have one question. You mentioned that you have 90 services, and I assume that you also have to, the user data, you have to have it in several places. Do you replicate the user data, and do you face any issues in replicating this? For example, when you push data and you want to call the user by name, you won't go to the user service to say what's the user's name, but maybe you'll have it somewhere around. Do you have such kind of use case, and how do you deal with that?
Yep. So the question is, if we replicate data between services, and how we deal with that. So actually, the example of a user profile, we store that in one place. There is a profile service which stores the user's name. Addresses are a bit more complicated because, well, all of these things we have to have history, but you may have multiple addresses, for example. So we store those in services that just deal with those things. And that does mean that, yes, if we send someone an email and we need their name to go on the email, we'll call the profile service to get their name. And that means you might have quite a large chain of services that need to execute. So what we'd usually do is we try and kind of abstract that up a bit so that we can do as many of these things in parallel as possible, rather than calling one service which now calls two services, which now calls three services. We realize that we need some of this data on all of these interfaces, so we can call all three in parallel and then call a final service that would send the email, for example. And that means also in some cases we can deal with partial failures. So an example would be if we're returning particular search queries back to the end user in the app, we do things like we look up at the items in the feed, we do transactions, we look up things at particular merchants, and I think if the merchants ones fail or the attachments that you've put on, we can tolerate that and we can return the search query, the search results without that like extra information, and then if the user taps on that search result, we can then request and actually try and get that data again. So it allows us to deal with like partial failure. We don't if we can avoid it. In this case, for a user profile, we have like one domain object, which is the user, and the user's like name and information. That is like there's one service that's responsible for that. And I'd say in a lot of cases that is the case. Underneath that, in Cassandra, we denormalize the data loads because that's the way that Cassandra works. But at a service level, no, we generally have one thing that's responsible for a particular section of our application. Cool. Anyone else? Otherwise, I'll be around all the time, and I think we have beer. Cool. Thank you very much.